So hello everyone, my name is Felix. I'm a PhD student in the University College Dublin. Today I'll be presenting a study on assessing the influencing factors on the accuracy of underage facial age estimation. My co-authors are Becker, David Lillis, Le-Khac, and Mark Scanlon. We are members of the UCD Forensic and Security Research Group. I will be presenting I will be talking a bit about the introduction of digital information and how it is collected in a crime scene. This will lead to the topic of digital forensic backlog. And then a way to tackle this issue is the usage of automated tools such as automatic age estimators. But not always these tools work accurately. There are certain influencing factors that hinder the performance of facial age estimation, such as facial expression, noise, makeup, and so forth. Further, we will discuss data bias, followed by the methodology we apply to evaluate the influencing factors. Then our data set that we collected, the cloud services evaluated, and the Pearson correlation criteria used to obtain the linear correlations between the error difference and each attribute. Error difference in this term is the difference between the ground truth age and the age predicted. Finally, we will address the results and conclusions. So today, everyone leaves behind a digital footprint, whether it be taking the form of social media, IoT, and surveillance devices. All these digital information are key sources of evidence and can potentially aid law enforcement investigations. There's a multitude of different ways that data can be manipulated in order to identify, locate, and classify individuals, whether if they're suspects or they're a victim or a civilian. So in particular for our study, we are going to focus on the underage group. A swift response to the detection of endangered minors is a critical objective, particularly now with the rapid growth of and declining cost of digital devices. Automated age estimation techniques are needed to aid these investigations, to expedite evidence discovery process and decrease the exposure to unlawful material for investigators. These techniques also show great promise in helping decrease the overflowing backlog of digital evidence obtained from the increasing number of devices and also in the online services. Automated facial age estimation is a crucial service that can potentially alleviate the digital forensic backlog. But what are the influencing factors that affect the accuracy of these age estimators for underage subjects? And can we analyze the trends within both strong positive and negative linear correlations? How do they affect the underage facial age estimation for different ages? These are just some questions that have been addressed in this study. So what is the digital forensic backlog? The digital forensic backlog is all about digital evidence that has been collected in a crime scene and stored in a digital forensic lab, awaiting to be processed by an expert. However, due to the lack of time and the availability of experts, there has been an exponential growth of devices, which has led to the digital forensic backlog. Petabytes of information of our lives are consciously being transmitted daily from various sources such as social media platforms. and communications via mobile messaging apps. Personal data is also collected surreptitiously from location-based services, facial detection or recognition capabilities by private or state-owned CCTV cameras, and activities recorded by internet-connected sensors. All this data can be used as evidence, and when collected for investigations are stored in the lab, waiting to be processed. Nevertheless, practitioners have become overwhelmed by the amount of digital evidence they must deal with. A high percentage of investigations in law enforcement agencies have to do with child sexual exploitation material, and the exposure to this content has proven detrimental. Therefore, we have proposed the inclusion of automated techniques, deep learning, artificial intelligence in digital forensics to assist the evidence discovery and the analysis. However, we have focused on age estimation, and there has been certain influencing factors for facial age estimation that we have studied. Facial aging on its own is influenced by several factors. We have extrinsic components such as the environment, habits, diet, makeup, and cosmetics. These extrinsic components have to do with external factors. Facial expressions are an example of influencing factors for facial age estimation. In a study in 2013, it was found that, for example, smiling, frowning, or surprise can generate facial lines that would be confused by wrinkles and would impact the performance on age estimation. The introduction of noise also alters the age estimation. It is a randomness that affects an image and mostly occurs during the digital capture or the upload of the image, say, in social media. In a study in 2012, it was determined that a simple alteration is capable of compromising the outcome of a biometric system. Later in 2014, some researchers demonstrated that the presence of certain imperfections, such as, spots, wrinkles, could result in the underestimation of the age due to them hiding these imperfections. So as we talked earlier this week, there was a talk on Monday about data bias by Rio. We also have identified some issues due to data bias. Biased databases are more commonplace. Therefore, trained models are unable to handle properly ethnicity, gender without bias, and thus cause the performance to decline. In previous studies, we evaluated the influence of gender in automated age estimation and determined that for 4 age prediction services, AWS, which is Amazon Web Service Recognition, Microsoft Azure, and Deep Expectation and Kairos, the accuracy for female subjects was lower than for males. So these offline and online cloud services that we used had the capabilities of granting us the predicted age, which we were able to evaluate. Now, for example, the offline deep expectation model was a convolutional neural network that was trained over 500,000 images from a dataset of IMDb that was correlated with Wiki. They had a performance of 3.25 years in terms of mean absolute error. This measurement, mean absolute error, has been widely used for age estimation and is the mean average difference between the ground truth age and the predicted age. So this performance is quite promising, and yeah, we did further work. In previous studies, the effect of aging has also been found to vary within gender, with male faces tending to age slower. However, in conclusion, models trained with unbalanced data set will produce biased results, thus leading to compromised accuracy. The methodology we used to evaluate the influencing factors. So in order to investigate the influencing factors on the accuracy of underage facial age estimation, we must first obtain a data set that's specialized in underage data. So initially we looked for other data sets that we could use. However, we found that there's lack of underage data sets and they are not fully labeled. Some labels, usually for age and gender, are just guesses, and this impacts in our studies. So what we did was we created the Visage dataset. It was created to address the shortage of adequate underage databases available to investigators. So this dataset contains the ground truth age of each image subject and will be utilized to identify the accuracy of the age estimators. Now, once we had the dataset, we were then able to process the images into certain cloud services. In this case, we used Amazon AWS Recognition and the Microsoft Azure Face API, two cloud services that are available to provide an age estimation and image classification for each image within the dataset. The ground truth age and the obtained estimated age from both cloud services can then be evaluated against the attributes obtained and identified by these services for each image. With the use of the Pearson coefficient, we are able to identify linear correlations between the accuracy of the age estimated and the attributes that were classified for each image. Therefore, we were able to identify some influencing factors of the accuracy of the underage estimation. So Visage is a web-based voting system that allowed several researchers to vote for an image to include it in our data set. So once it had 3 positive votes, it would be included. However, sometimes we will get 2 positive votes, 1 negative vote, and this had to be resolved by a quality assurance agent. So this data set was curated. And as you can see on the right-hand side, bottom right-hand side, that's the distribution of the counts of subjects per age. And throughout the age, we can observe there's an exponential decay of the amount of images. Nevertheless, we were able to obtain over 19,000 images. So these images come from Flickr, they're Creative Commons, and they're from 1 to 18-year-olds. They're specifically for underage. And these images were labeled by the author. So the author would usually put the ground truth labels for the images. They were usually in birthday parties, and we were able to easily identify these images with their age and their gender. And as you can see on the bottom left, this is an average of our data set per age. So more or less, us humans were able to, we have quite a good accuracy on detecting facial age. Our performance ranges from 2.07 to 8.62 in terms of mean absolute error. And this can vary whether we are assessing someone of our own age, so the performance can improve. This is more or less how our data set looks like, and following to the next slide, the cloud services used, AWS and Microsoft Azure, we were able to obtain certain attributes such as glasses, eyes, the mouth, accessories, headwear, head poses, roll your pitch degree, all these attributes of the face, and also additional information such as the quality of the image, where we would have noise, blur, brightness, occlusion, exposure, also resolution. And we were finally also able to obtain human biometric attributes such as gender, facial hair, emotion, and age. Now we can see the results of the degrees of correlation here. So for the error difference, we had to select an error difference greater than 5, because when the error tends to be close to 0, we weren't really able to obtain much information about, say, strong or strong, mild, or weak correlations. So what we did was we grouped the correlations in 3 groups. We have strong correlations, mild correlations, and weak correlations. Well, based on another study of digital forensics in 2014, they did this classification. So they defined strong correlations as from 0.5 to 1. And these can be seen depicted here in this table. They are in black. And then we have the group of mild correlations, which are from 0.49 to 0.3. These mild correlations, you can see in this table, they're in gray. And finally, we have the weak correlations from 0.1 to 0.29. These have been omitted from this table. For example, the exposure, which is the amount of light that reaches your camera, we can see, for example, that there, while being an underexposure, or let's say a bad exposure, there is a higher degree of correlation with the error. Whereas if we have a good exposure, there is an inverse correlation, in this case, negative. And also throughout the ages, we have seen some correlations, strong and mild correlations for hair attributes. For example, sideburns, mustache, and beard, we can see that there are correlations. But this might seem weird to see, for example, mustache and beard for 1-year-olds. But due to the data set we used, there are certain images, because they were taken from birthday parties, many images have, say, cake on the face, or there are also children with fake mustaches or fake beard. So this presents a challenge to our research, and because it decreases the accuracy of say, the age estimation and algorithm. We can also see certain mild correlations with, say, the emotion, content, anger, sadness, and fear, disgust, and surprise also. So we found, for example, that neutral faces are usually have a low degree of correlation with the error. That's why we might. That's why maybe when we are asked to take a photo of the passport, we are asked for a neutral face, so it doesn't impact with certain features. And we also have, for example, occlusion. Occlusion is a factor that influences a lot. So say we have say we have artificial devices like glasses on our face that cover our eyes, say swimming goggles or reading glasses, sunglasses, this will also have an impact on the accuracy. Whereas when there are no glasses at all, we can see a decrease on the error. And following with the results, we can see on the left Microsoft Azure Face API, whereas we have on the right Amazon recognition. These are the correlations per age with an error difference greater than 5. So if we go from top to bottom, well, this one represents the error when it correlates with itself, so it's not really meaningful. But we can see that there are certain strong correlations here, whereas on Amazon recognition, we don't really have strong correlations. And then we can see there are certain attributes with mild correlations. However, the majority are within the weak correlations, positive and negative weak correlations. And for Amazon recognition, we can also see that there is solely weak correlations. And finally, our conclusions. So in the predicted ages that are close to the ground truth age, say the error difference that tends to be 0, there are actually no attributes with strong correlations. And the majority of strong correlations found between ages 1 to 10 are due to the quality of the image, emotions, and human biometric factors. The error difference was also influenced by the quality of the image, good exposure level, and low level of noise. And a bit of our future work. Sorry. Okay, I won't skip the future work, but yeah. So for our future work, we would like to isolate influence and factors to improve cloud-based predictors. We would also like to create robust models that address the performance issues due to facial hair, makeup, noise, and emotion variance. So I'm quite an advocate of the no free lunch theorem, which states that that a model is not good for all the problems. So I would just separate the problem. For example, create a model that is an expert for makeup, but for certain age range. And then we would like to explore also non-linear correlations that we didn't do in the study. And finally, we would address the issue we would like to address and tackle data bias. And well, I want to thank everyone for your time. And we have a link there on the top right, which has a QR code where you can register the data set we have available, the Underage data set, which currently is in progress. We have over 19,000 images, and we're happy to share with whoever registers. Thank you very much.
Thank you very much, Felix. It's been great. We have a few questions for you. So Cyril is commenting that it appears to be no diversity in the color of the faces of the images. And he's asking if that's due to the composition of the data set.
Yes. So yeah, exactly. We also had this this issue because we collected the images from Flickr. We didn't really analyze, say, ethnicity, but we did run a skin tone analyzer. And this one was able to sort of tell us that there was a bias on other certain skin tones.
Okay, So Cyril is commenting as well that because you are using Amazon Web Services, so that is a process that is kind of transparent for you, right? I mean, it's kind of a black box. So you don't really know how the classification is working. Would you improve it using your own algorithms, or are you planning to have a collaboration with Amazon, given that they are in Ireland as well?
Oh, yeah, well, it would be fascinating if there were a project with Amazon. However, currently we are more focused on, because we're focused on cybercrime investigation, so we're, say, focused on specifically the issue of child sexual exploitation material. So this is composed of two components, a nudity detector and an age detector. So we are more focused right now on the age detection. However, in the future, if we have the opportunity, we would collaborate, and we have the knowledge to create other models. And
great. So probably you have time for a last question. This one is from me. So given the huge volume of work that forensic analysts have, do you think if it could be better to have a classifier which is underfitting or a one that's overfitting? Because in one case you will have some false positives, and the other case you will have less data to process.
Correct. Yeah. So if we will focus on a model that would only address age estimation, so we will have to analyze this age estimator. Now, it is quite a difficult problem to, like, it's quite difficult to estimate the age due to several factors, such as the environment, the habits, diet, but we will always have certain, let's say, a certain tolerance or threshold where we can address, and we can filter images that are within this threshold. So we can only focus, say, underage images or adult images. So yeah, but it would be like it wouldn't be a system that will have the final say. It will just assist the investigator.
Okay, that's great. Thank you very much, Felix. It's been a very interesting talk.